Hello.
Hello. Hey, Sarah.
Hi, Peter.
Hi. It's good to have you back home.
I'm back in my natural habitat.
And I believe your hair is different than the last time you made a video.
We're very
It's
we're very blue right now.
we're-
This wasn't planned, by the way, but you are maximum saturation blue, and I just wanted to match my hair today. So welcome to Connections Museum, very blue edition.
blue day. Okay.
Yeah.
So what I wanted to do with you today, Sarah, was talk about some of these things here. Now, these artifacts are models, reproductions of things that Thomas Watson made for Alexander Graham Bell
Okay.
for the 1876 Centennial Exposition in Philadelphia. And in fact, we have some pictures of what it looked like back then that I'll put on the screen. So the thing about these is that we have a really important anniversary coming up. March 10th.
Okay. And which one is that?
March 10th is the world's first telephone call.
Okay.
At least if you believe the standard history. Now, I think the standard history is actually correct about this, and maybe in another video we'll get into some of the controversy and debate. But March 10th, 1876, that is when Alexander Graham Bell said to Thomas Watson over the telephone, "Mr. Watson, come here, I want to see you." And Watson heard him for the first time ever.
Right, right. So you talked about some of these things in your last video. You talked about the musical telegraph thing.
Right.
So I know what that is now.
Yep.
This is a thing you shout into.
Yep.
Am I right?
That is correct.
Okay.
Yes.
I don't actually know what this is or what this is.
All right. So this is also a thing that you shout into. You shout into that hole in the bottom of it there.
Okay. Yep.
And that's supposed to vibrate this diaphragm here and make this little metal piece go up and
Oh, right. Okay. So this is like a drum head
right
here, which is weird. It's cotton, but I think it's probably sheepskin or something originally. And that drum head vibrates this little paddle here attached to. Okay, I see what's going on.
Exactly. So according to Bell's notebook, this was the first thing that they tried, 1875-ish sometime. And it kind of made indistinct sounding human-like sounds, but you couldn't understand what was coming out of this. So we're going to put this aside because that's not what I want to talk about today.
Okay.
And then this thing here, this is from after March 10th. After they improved this thing a lot, it turned into this thing.
Okay, so we're back to the drum's head, drum skin thing, and I assume this would be a magnet or electromagnet.
Electromagnet in here, exactly, vibrating this drum head, but now you've got sort of a cone to direct the sound into your ear.
Okay, all right. So we have the cone of sound direction. So I guess you'd hold it like...
You'd hold it like that, right? Exactly.
Okay. I'm listening to the seashell.
Yeah. Now, the sad thing about this device, it's a nice looking reproduction, but look at that. There's no actual coil in here.
Okay, so purely for looks,
purely for looks.
Okay,
yep.
There is no functionality to this thing.
No functionality to this thing at all. Yeah. So we're not going to look at that today either.
Okay. Okay.
And that leaves us with these two devices here.
Okay.
Now, this was what he was using for his musical telegraph thing, as you said, his harmonic telegraph, but he was also using it as an earbud.
Okay, I'm suspicious, but...
So was I. But unlike those other things, this thing was designed to actually be a real reproduction that works and everything.
Okay.
So the first thing I thought I would try to do with you that would be fun is try this out and see if you can hear anything coming out of it.
I'm into it. Let's do it.
All right, so let's push this out of the side for a moment. Oh, by the way, I was going to point out, these things have these little tags on them that say that they were manufactured, reproduced by Bell Telephone Labs, 463 West Street in New York.
Right, so they apparently, if this is to be believed, had a nice little model shop there with some cabinet makers whose job was to build these reproductions.
Yeah. And I think that roughly dates this because Bell Labs was created in 1925, so it couldn't be from before that.
Has to be after that.
Right. and they moved from New York to New Jersey in 1960.
Right.
So it has to
Right.
be before that.
Right. Right.
Anyway, okay.
So we have just like an audio interface, right? It's just like a USB.
This is a little audio amplifier that's
Okay.
being fed by USB out of my laptop.
Okay, so it
Right.
shows up as a sound card.
So it just shows up as a sound card,
Okay.
right?
Okay.
And it's driving this device here at its absolute maximum volume.
Right.
And I'm going to play, and don't look.
Okay. Nope.
You
I'm
don't
not
wanna
looking.
see?
I can't see.
All right. Let's see here. Hold it up to your ear. Now it's kind of tricky because you have to get it right up against your ear
Without it touching.
without it touching.
Okay, so I can hear like a tiny ringing sound, an intermittent ringing. Oh, I could totally hear a voice. Oh, there we go. It
So-
sounds like an educational video.
So now read the closed captions and see if you can understand what he's saying when you read the closed captions.
I absolutely can. Yes. Okay, now I'm going to look away again. I want to see how psychological this is. Turn your laptop away so I can't see the captions. Information in a pattern of holes and no holes. 0.
Very good. He's talking about punched cards now.
Yeah. Oh my God, that's so wild.
Isn't
Okay.
it?
So it's weird. You were right. I gotta say, you were right. Actual demonstration, you have to have it just right. Like I could only hear this sound, like the dinging sound until I had it positioned perfectly.
Right. Which is clearly one of the problems with this thing is
Yeah.
that it's a loudspeaker with a very strong fundamental frequency that it likes to go ding, ding, ding at. Right.
Yeah. And that's what I heard. I heard like little, like it was almost like a tiny little bell, but like when I had it just perfectly right, I could totally make out the words.
Right. That was the receiver
Okay.
that they used on March 10th of 1876. This thing. Which is a little hard to believe,
Yeah.
but
I mean, I hope it was quiet in Bell's lab.
it probably was a lot quieter than it was in the
Yeah.
museum because, no cars yet. So now this thing is the transmitter that they used with that.
Okay. Did you measure the impedance of this, by the way? Do we know?
I did. It's 121 ohms,
Okay.
which is, a lot higher than a modern normal loudspeaker would have.
Yeah, this is probably like 4 ohms.
This is designed for 4 to 8. So
Yeah,
I'm
so-
kind of abusing this little amplifier,
you're right.
but oh well. All right. Actually, we're going to disconnect this now because we're done with that experiment. Here we have Bell's notebook from March 10th, 1876. And that's the whole wiring diagram.
Okay.
A couple of batteries.
There's S.
This thing, that's this thing, S,
Okay.
right? And then this looks a little different than that. What we have here is actually the improved version of this
Okay.
that doesn't show up in the notebook until a few days later.
Okay.
So one of the questions I had for you was, I guess I could try to make a reproduction of that out of a Tupperware dish and some water and
Yeah.
stuff and see if it works.
I think you should try this first.
I-
Right? Because
yeah.
this is a thing that exists.
Right.
I think if anything, it'll be harder with your reproduction. I think this could be made to work.
Possibly that can be made to work. So that is the whole goal, Sarah, is that, and I haven't done it yet.
Okay.
I wanted to talk to you about it first, but I want to try to actually recreate the March 10th, 1876 phone call with this thing and that thing.
That's going to be so cool. So again, this is just a diaphragm with a little cone that you can shout into, right?
Right.
And then it's got these, it's almost like tuner. I keep using the drum analogy because I'm a musician, but these are like the tuners on a drum, right? These are going to tighten that that diaphragm there.
I'm not sure, actually. If you look at what they do, they just increase or decrease the distance from the bottom of the cone to the diaphragm. And I don't know why that was important, but it's in his sketch.
Wait a second. No. Because this diaphragm on this thing, IMO, is way too loose to be any good.
Well, as you're about to find out, I've already tried this out
Okay.
at home on my bench. And yeah, I think you're right. That diaphragm is way too loose.
Like, you need, in order to actually like capture sound, this is like flapping in the breeze.
Right. But let's look at it anyway, what it's supposed to do, right?
Okay.
So you've got this little cup down here
Yeah.
that had hydrochloric acid and water in it.
Mm-hmm. Danger juice.
Danger juice, yeah,
Yeah.
exactly. And you had this little needle, and you had this really thin little wire here.
Right.
I don't know if you can even see that. And that thin little wire is connected to this post over here. And then the cup is connected to this post over here.
Okay.
And that is what is supposed to change the resistance of the circuit based on the sound coming into it, right? Because the sound makes the little needle go up and down in the juice.
Right.
And when the needle's further down in the juice, the resistance goes down, and when the needle's further up.
Is the acid juice the same as like the carbon in a standard old telephone microphone?
Exactly.
Okay.
This is a primitive and not very good version of a carbon microphone.
Right.
Right. Just to recap for folks, there's basically a few different ways you can make a microphone, but the idea is for any of them, you have to change the sound waves in the air into some kind of electrical wave that you can then measure, right? And so you can either try to change the resistance,
Right.
that thing, or a carbon microphone. You can change the capacitance. You can make a microphone out of a capacitor, and that just like vibrates the plates closer together. So then you're changing the capacitance, right? Or you can use a coil of wire and some kind of magnet, right?
Right, to create
a varying voltage,
mm-hmm.
and that's called a dynamic microphone.
Right.
Right. So you either have to change the resistance or the capacitance or the voltage. So this thing changes the resistance.
And yeah, and like for like most of the 20th century, the standard telephone mic was that kind, where there had to be some current passing through the mic, through the transmitter at all times, and then that transmitter would just change the resistance to that current flow, and that's how it would impart the speech upon the wires.
Exactly.
Yes.
That's exactly right.
Yes. Science.
Yeah. Okay, so what we're going to do, though, because people might be wondering why there's tuning forks sitting there.
You haven't told me, and I'm actually wondering why there's tuning forks.
Okay, so let's look at his notebook again.
Okay.
Early February, he's playing with all kinds of things that aren't the telephone. He's still working on his harmonic telegraph idea. Then he has to go to Washington, D.C. to talk to the patent lawyers about this famous patent. March 7th, 1876, return from Washington, D.C. March 8th, 1876, he's dipping tuning forks into cups of water.
Cool.
Why is he doing that? I think he was trying to make one of these. He was trying to make an audio frequency oscillator so that he could test his speaker to see how it would work.
And they obviously didn't have the technology.
He did not have an actual audio oscillator, but his idea was that if I dip tuning forks just right into a dish of conductive water, the fork will like bounce in and out of the water and put the tuning fork's frequency onto the wire. Okay.
All right. So did that work? Like,
he says it worked. In this notebook, he says he could hear the sound coming out of the speaker afterwards. I tried this at home with these.
Doubtful.
Did not work for me at all. The problem I had was that the moment this goes into the water, it stops vibrating like right away.
Right, because the whole thing is like you have to use this part of the tuning fork to transmit the sound. So like the way you do it is,
right.
and like I can hear it now because I'm using the bass.
Bone conduction
Yeah.
right there, yeah.
Ooh, it's inside my head.
Yeah.
Yeah, anyway.
So he might have had steel tuning forks. These are aluminum, so they were a little heavier. Maybe they vibrated a little. Anyway, I couldn't make it work. But the whole point of it is that he has now shifted. He got news on March 3rd, his birthday, that the patent was going to be approved. And
Okay.
on March 7th, it was approved. So this is a giant weight off his shoulders.
Yeah.
Right? And so now he can put the whole harmonic telegraph thing aside and really start thinking about his...
And jiggle some water.
And jiggle some water. Really start thinking about his telephone idea, right?
Yeah.
So at the end of that day, he's playing with all these tuning forks all day. At the end of that day, he draws this picture here for the first time under thoughts, right?
Okay.
It says, it seems like the sound from M is loudest when the metallic surface B is largest. That's the bottom contact there.
Yeah.
And the vibrating surface in contact with the water is the smallest. So he's kind of figured out, oh, I want like a big conducting surface on one side and like barely dipping in on the other. And he draws that picture and he tells Watson to go make that thing for him.
Yeah. Yep.
March 9th, Watson comes back with the first version of that.
Mm-hmm.
They try it out. They hear like indistinct muffled sounds,
right.
but it doesn't quite work. He sends Watson back March 10th, slightly changed version of it. And they try it out. And here you can see, I then shouted into M, that's the transmitter, the following sentence: Mr. Watson, come here. I want to see you. To my delight, he came and declared that he had heard and understood every word.
Cool. Cool. So just an aside, I just wonder how soundproofed the rooms were, because like it was like an attic, right?
Well, that's a good point. So he was worried that people were spying on him when he was working in the attic over the Charles Williams shop. So he went and rented 2 rooms in Exeter Place.
Oh, okay.
So now he's doing this in his apartment, basically, with Watson. So he's got a little more privacy, and there's not like machinists downstairs hammering and...
Okay, that makes more sense.
Yep. And then he plays with a tuning fork idea a little more.
Mm-hmm.
Now he's trying like 2 forks at once. Can I make like a chord here?
Yeah. Cool.
Here we are, March 14th. And for the first time, we have a diagram, which is basically that thing.
Right. Yep. Wild.
Yeah. So I've already played with that. And we're going to watch this video together, and then we're going to talk about it a little after that. Because a liquid transmitter is kind of like a carbon microphone from an electrical point of view, and I already know a good circuit for a carbon mic, that will be the starting point for my test. Here's a typical circuit that you would find in an old-fashioned wooden wall phone with a carbon transmitter. When the phone is off hook, current flows from the battery through the carbon element and the primary winding of an audio transformer, which they used to call an induction coil. That induces a current in the secondary winding of the transformer, which also blocks the DC from the battery and embiggens the AC signal so it can go out on the line. An old-fashioned induction coil looks like the thing on the left, but I'm just going to use a cute little modern audio transformer which does the same thing. So I just need to get rid of the parts of the circuit I don't need and put the liquid transmitter in place of the carbon one, hook up my oscilloscope to the secondary output, and then I will use a speaker connected to an audio signal generator to make different tones into the liquid transmitter and see what audio signal the oscilloscope can pick up. I think I have everything hooked up here now. I have my signal generator set for a 200 hertz sine wave output, and that's the blue trace that you see here on the oscilloscope. I think I mentioned in the video about Bell and Gray and their patent race that Bell would certainly have killed to have had an oscilloscope. It would have made it a lot easier for him to figure out what was going on. Although he did have a thing called Koenig's manometric flame apparatus, which is what he used to make these sketches of the waveform that you can see in his notebook. I'm not going to go into a lot of detail about the flame apparatus, but it is kind of an early version of an audio oscilloscope. And Bell had modified it so that it would pick up a signal from one of his vibrating reed devices. Anyway, I have my bench supply set for 3 volts, about 40 milliamps max, and that is feeding the primary here, and then the output of that little transformer hopefully will produce a signal on the oscilloscope on the yellow trace. And this is just saline solution. Bell, as you might know, used dilute sulfuric acid in his liquid transmitter. But the notebook shows that he also tried some other things, including cod liver oil, salt water, mercury, and soapy water. And he found that salt water works just as well as the sulfuric acid. So that's what I'm going to use here because it feels a lot safer to me. And I'm going to squirt some into the cup now, and hopefully I can get in there without making a big mess. And now I'm going to adjust the level of the liquid cup here so that the needle is just barely dipping into the water at the top, which is what Bell recommended. Okay, that looks good. Let's see what happens. And so now I'm going to turn on the power. And we've got about 23 milliamps flowing. That seems reasonable. So now let's plug in the speaker. See what kind of a signal we get. Nothing. Nothing but noise. Well, that's disappointing. Let me try changing the frequency and see if that makes any noticeable change. Oh, wait, I think I can barely make out among the noise a tiny little signal. Huh. All right, well, okay, I took away the cone here, and if I tap the top of the diaphragm, that does cause a little bit of a signal. So I think my electrical connection is good. I suspect that the problem is with this diaphragm in here. I don't think that Bell was using starched cloth. I'm not sure why the labs used that. Bell doesn't say explicitly in his notebook what he was using, but in an earlier entry about a different transmitter, he did mention that they tried gold beater's skin, which is basically sausage casing. It's made from the intestines of cows. So I'm not going to use sausage skin here, but I'm going to see if I can try swapping that diaphragm out for something else, and maybe that'll work better.
Okay, so I think you're dead on about the diaphragm because, like, Bell had to have known that a tight diaphragm was required for transmitting sound. I mean, like, humans have known that since before writing, right? Or not for transmission strictly, but we've had drums since like before the advent of writing, so we understand how that works. And I think that probably, if I had to guess, that the labs was not trying to make a working model, so they didn't exactly try to make a great diaphragm, and or in the 80 years since this was made, the formerly tight diaphragm has just gotten, it's loosened.
Yeah.
And so to what I was saying earlier, on a modern like snare drum, there's a ring that the diaphragm is pulled against. So if you ever see someone like tuning a drum, what they're doing is they're squeezing that diaphragm down onto the ring or the lip of the drum, and that's going to adjust that tension. And this thing has no mechanism by which to do that. I thought it did, but it doesn't. So this is just a piece of cloth with some wax twine wrapped around it.
Yeah.
It's going to be hard to get that tight.
Yeah. This is a pretty nice little model here, and I kind of don't want to mess with it. But fortunately, we have another one.
Which is less nice?
Which is less nice because whatever they made that diaphragm out of like totally cracked and got brittle and failed. So it already didn't have one. My plan now is I'm going to figure out something, I'm not sure what yet, but some kind of rubber or plastic probably, to make a new nice drum tight diaphragm out of, and put a little new needle on it and hook it up and see if I can't actually get some sound to come out of it. And if I succeed, then I'm going to record it so you can all hear it too.
That's very cool. I love this. I think what you need is you need to recreate. I don't know that you're going to be able to get it tight enough just by hand. It's going to be really fiddly and hard to keep the diaphragm under tension. And I think you might need to make a lip that presses against the diaphragm from the inside that you can then tighten down.
We've got it apart now. And yeah, so this is the part that needs the diaphragm stretched over it.
Right.
Right. And so what I'm thinking, I have to see what I can do when I get back to my bench. But what I'm thinking is, this screw has to come out now too because it's in the way. Find some piece of material that I can like stretch really tightly and hold it down with something on the bench, and then use another piece of waxed twine to tighten it up in this little groove here, so that it's pre-tightened before I try to clamp it down. Does that make sense?
Yes, it does make sense. It's gonna be tough.
This is pretty much a pretty accurate reproduction of what you finally see in his notebook. And they also have the original one of these that Watson made for Bell in 1876 at the Smithsonian. It's not on display, but you can go to their catalog and see a picture of it.
Yeah, they even went so far as to like wire this thing up. Like if this was, that's weird. If this was just like a model that was supposed to sit behind glass and like attract onlookers or something, they didn't need to actually make it electrically functional.
Right.
Weird.
Yeah. So that's the plan, and hopefully the next part of this video is going to be at my bench, me trying to make this work. And then if everything really goes well, the final part of the video is going to be me talking to Sarah over that thing and that thing.
Cool. Do it.
Will Peter be able to make a diaphragm for the liquid transmitter that works? Will Sarah be able to understand the transmission? Will they be all happy, or will they be disappointed by the result? Stay tuned for the exciting conclusion, set to premiere right here on the Connections Museum YouTube channel on March 10th.